I want to do a quick recap of what we talked about last week at the start of class, or kind of towards the end of class. So we talked about how this class is thermodynamics and heat transfer. We're starting with thermodynamics, of course. We talked a great deal about units and dimensions. Units are extremely important. It's a way we can communicate with other engineers and scientists so that we're all on the same page. It's also an excellent tool to figure out if you have an error in the problems that you're solving. So I cannot emphasize that enough. And then we also talked about types of thermodynamic systems. Does anybody want to volunteer and describe a closed system? Does anybody remember? What cannot leave a closed system? Mass. Yeah, that's great. Who was that? I heard a voice generally in the middle of the room. You? Okay. Awesome. It's John. It was you, right? John. Jack. Mike. What? Mark. Yes, sorry. Great. Thank you, Mark. Does anybody want to volunteer what can come in or out of an open system? Yeah. Yes. Great. Okay, awesome. So I think we didn't really get a chance to go over these printed examples at the end of class. So we'll do that now. So these are two examples of an open system. So here we can have mass and energy coming in and out. So we have airflow coming in, and then we have exhaust gas coming out, as well as fuel coming in. So these are all mass flowing in or out. And then we also have energy coming in and out through the drive shaft, which is here. Okay, great. And then here's the cross-sectional view of that same system there. Okay. A couple more things to say about control volumes. So that is kind of how we contain an open system. So the boundaries of a control volume are called a control surface. A control volume can be fixed in size and shape. Which is the case of something that is kind of a fixed geometry. So if you have a nozzle or a car radiator, for example, those are kind of physically rigid structures. So you would want to fix your control volume in size and shape strategically. Or you could have a moving boundary. And that might be something like if you were having a balloon being inflated, or the space between an engine piston and the cylinder. So you have a volume that's moving. And typically you'll decide between a fixed or a moving control surface, depending on the problem that you're evaluating. So this is all about strategy. You can always do either one, but the math gets more complicated if you choose wrong, right? Okay. In all of thermodynamics, the thermodynamic system must be defined clearly and specified at the beginning of the analysis. This is super important. So this is going to be like the first step that we do when we start tackling problems. Because if we don't do that, equations like conservation of mass or momentum or energy is pretty much meaningless without knowing what our system is. All right. Okay, so let's do a couple of examples. Let's consider some systems and decide whether it would make the most sense to consider them as open or closed systems. So the first one is a light bulb. What do we think? Open or closed system? Closed, yeah. Why? Any ideas for why? Oh, yeah. Right, yeah, so mass is staying contained within that system. Energy comes and goes, but the mass stays fixed, so that's great. Remind me your name? Leo. Cool. Thank you. All right, what about a gas lawnmower? Open, yes, great. Thanks, Mark. Can you, or you or anybody else, can you justify why you'd want to use open instead of closed?
Gas is leaving the system. That's the.
Right. Yeah, so when you have, it's just like the engine example that we looked at over here. So we have an air intake, we've got fuel coming in, exhaust coming out. So we have fluid flows or mass flows, in other words, in and out of that system, in addition to the energy. Fantastic. What about this third system that I have drawn here? Any ideas on this one? And you could kind of look at it from a couple of different viewpoints. So what if, case one, what if we want to look at one tank, either one? So for example, if we just wanted to look at tank two, and this is our control surface, would this be an open or a closed system, do we think? So these are two tanks connected with some duct work, and there's a valve in between. So presumably things are passing between the two tanks, right? So if we're just looking at the one side of it, what is happening here? Is anything leaving or coming in? Maybe? Yeah, so we could have oops, flow coming out. So we should use an open system in this case. Does that make sense? If we instead consider the whole thing, so both tanks included with the valve in between, so the entire assembly, I don't want to call it system because that's confusing. So entire assembly, both tanks, valve, and connecting pipe. Then what about that? And let me draw. What kind of a system would that be? Closed, yeah. So we've got no mass leaving this now, assuming that nothing here is leaking. So this would be a closed system, assuming no leaks. Fantastic. Okay, so this is all I have about open and closed systems. It seems like we feel pretty good about this, but are there questions? Good? Okay, great. All right. Okay, so now we're gonna introduce some basic concepts that are gonna be useful to us when we're analyzing thermodynamic systems. So this is a lot of definitions that we're gonna go through, okay? Okay, so there are two approaches to studying thermodynamics. One is a microscopic approach. This is also called statistical thermodynamics, and it's concerned with the structure of matter. So we're looking at the thermodynamics of things kind of in a very close-up viewpoint. So we're looking at how individual atoms are interfacing with one another and so on and so forth. And opposite to microscopic is macroscopic. So that is the other approach. All right, and so this is what is known as classical thermodynamics. So that's what we are going to focus on in this class. So we're gonna assume that everything we're considering is zoomed out enough that we can kind of neglect all of the variations that are happening if we were looking at things on a particle or atomistic level. Okay. In other words, we don't need to have knowledge of individual particles, and we can evaluate things from observations of an overall system. Okay. There we go. Okay, so we're going to concern ourselves with aggregate behavior and properties that can be perceived by our senses or measured with instruments. All right, so things like pressure and temperature. Okay. Our next definition is property. So this is a macroscopic characteristic of a system and includes things like mass, volume, energy, pressure, and temperature. And it's a characteristic like those things where we can assign a value to it at a given time without knowledge of the previous behavior of the system. All right, so these are things that we can measure without knowing anything about the history of the system. All right, there are quantities in thermodynamics that are not properties, so things that do depend on the history of the system, and those are things like the mass flow rate. So if you have a rate, you have to know something about the previous time step. And then energy transfer by work and heat, for example. Okay. All of the properties that we care about in science broadly and thermodynamics as well are going to be able to be classified as either intensive or extensive properties. Have we heard of these terms before? No? Okay. So an intensive property is a property that is independent of the size of the system. So these are properties that don't depend on the size of the system. Can anybody think of a property that you can think of that wouldn't depend on the size of the system? So it doesn't matter how much of the thing you have, the property is the property. Yeah.
Specific water. Is that like a
Yeah, that's good. That's a good one. So specific heat. Can you remind me your name again? Pablo, thank you. Specific heat, that's a great one. Any others? Sorry? Oh, like the element of it? Sure. So atomic structure. Yeah. Density, great. What's your name? Michael. Thank you, Michael. And what was your name? Sorry. Ethan? Thank you. Any other ones we can think of? Yeah. Sorry. Oh, color. Yes, great. What's your name? Thanks, Owen. Yep, that's a good one. There's a couple more. I have two more at least that I want to include here. Yeah. Oh, gravity. So gravity is not quite a property, but I agree with you that it doesn't matter like the amount of the thing. But that is an interesting one. It is a constant. What's your name? Johan? Okay, thank you. The two that I was hoping to get to also are temperature and pressure. Okay, So all of these things, it doesn't matter how much of the material that you have in your system, the property is the property, okay? All right, in contrast to this, we can also have extensive properties, which is just the opposite of this. So this is a property that does depend on the size or the extent of the system. That's where extensive comes from. So these are properties that do depend on the size or extent of the system. Can anybody think of properties that we tend to care about or measure that would depend on the size of the system? Volume, yes, good. Any others? Yeah. Mass, great. Anybody have any other ones? I have one more listed that I want to put on the notes. Yeah. Heat capacity. Heat capacity, I actually believe is intensive. So heat capacity is a material property, right? So I'm going to add that one here though, because that is a good one. And that'll come up, capacity, that'll come up a lot when we get to heat transfer as well. Energy is also one, right? Okay, does that make sense? Intensive versus extensive? Yeah.
Pressure.
So that's a good question. I was actually wondering if anybody would ask this. So like, are you thinking that if you squish down like the size?
A lot of air in a large system, pressure would be different.
Right, the ideal gas law. So pressure is intensive. Let's see if I can articulate this in the right way. So if you have a system, imagine you have a system, it's the same system, and let's say it's a balloon at a given pressure. If inside of that balloon you just were able to isolate like a small little subset of it, that would have the same pressure as like if you were to include the entire balloon. So that's the difference. But you're right, in general, you know, like the size of the system can affect, or like the size of the system and how the boundaries are acting on it can affect the pressure overall. But does that distinction make sense? Okay, it's a great question. Other questions about intensive and extensive properties? Okay. We also are going to make use of specific properties. Have we heard of this terminology before, maybe in chemistry? I know there's been mention of, I think, specific heat. So I know we use this language at least in some capacity, but a specific property, the specific just means that it's a property per unit mass. And so if we have some property, let's call it capital B, usually we're going to refer to its specific, corresponding specific property as the lowercase letter of the original property. So we'd use lowercase b. There's obviously some exceptions to this. So we would have in this example, the lowercase b is just the uppercase b divided by m. Obviously, there's exceptions to this because capital T is temperature, but lowercase t means time. And then capital A is area and lowercase a is acceleration. So for A's and T's, we don't mean specific when it's lowercase. Okay. All right. State is another term that we're going to use quite a lot in this class. So a state is a condition of a system which is identified by means of its properties. So things like pressure and temperature, for example. And at a given state, all of the properties of a system will have fixed values. If the value of even one property changes, then that means the state is going to change to a different one. Okay? All right. Thermodynamic equilibrium. So a system is in thermodynamic equilibrium if it maintains four things. Those four things are thermal equilibrium, mechanical equilibrium, phase equilibrium, and chemical equilibrium. And by equilibrium, I'm saying that each of these four things is not changing, right? We're in a balance. All right. We're also going to make use of the word or the term process. So process refers to when any of the properties of a system change, the state changes, and then the system is said to have undergone a process. So essentially what I mean by this is if we have some property A and some property B. So often you'll see like pressure and volume or pressure and temperature on a chart like this. And we will have two states. So if you remember, a state is when you have both of your properties are fixed. And once one of those properties changes, you're in a different state, right? So each point on this chart represents a different state. So I have two states here. And so when we go through a change, which could look, for example, like this transition from state 1 to state 2 is called the path of a process. So this is a process path. And there's generally more than one way to get from state 1 to state 2. So we could take that process path in red, or we could do this one in purple. So this, I guess it's blue. I don't know. Not sure what color that is. This is a path of a different process. From state 1 to state 2. All right, so 1 is our initial state. And 2 is our final state. All right, and so we have our state 1 and our state 2, and then we can take a process path to get from one to the other, but they could be different. Does that make sense? Okay, cool. We can observe what is called a quasi-equilibrium process. So this is a process in which the deviation from thermodynamic equilibrium is infinitesimal. So it's infinitely small. Infinitesimal. This is one of the words I cannot spell while speaking. So you can think of this as a process where the change is so slow that the system essentially has time to reach equilibrium at each part of it. Okay. And that means also that the properties are going to remain approximately uniform throughout the whole system. Okay. All right. We will also study cycles in this class. So a system has undergone a cycle if it returns to its initial state at the end of the process. All right, so for this to count as a cycle, the initial and final states have to be identical. It's the same state that you're starting and ending with. All right, so if we go back to our property A, property B, chart, but this time I'm going to put pressure on the vertical axis and then volume on the horizontal. A cycle will look something like this. So we'll start from state 1 and go to state 2. This is what our path will look like, for example. And then we'll take another path from 2 to 3, a path from 3 to 4, and then we go all the way back to our original state 1 through this last process from 4 to 1. All right, so this is a totally closed, the paths are closed. We start and end at 1. That's what makes it a cycle. Okay. We're also going to use 3 terms quite a lot: isothermal, isobaric, and isochoric or isometric to describe processes. And so it always helps me to remember what each of these means to talk about kind of the root words of where they came from. So they all have iso in the beginning. Isos is a root word that means equivalent or same. Therm, we've already talked about, that means temperature. So an isothermal process means that the temperature is always the same. Or in other words, we can say that temperature is a constant, right? For isobaric processes, baricose is the root word involved in this, and that means pressure. It's also why we call a pressure measurement device a barometer. So it's the same root word for that one. So similarly, this means that throughout this process, our pressure is going to be held constant. All right, and then for an isochoric or isometric process, choros is a root word that means volume or space. All right, and so this means that for this process, our volume is constant. Any question on those 3? Sorry, I know doing the terminology is kind of boring. We're almost through it. Okay. Now we've mentioned that specific variables have to do with dividing by mass, right? So a special one that we care about a lot in this class that we're going to make use of is specific volume. And this one comes from essentially from density. So hopefully you're all familiar with density already. Density is just mass over volume, right? And this typically has units of things like kilogram per meter cubed in SI units or pounds of mass per cubic foot in English units, and so on and so forth. And when we're talking about density, technically density could change over space, right? So if that were to happen, we would compute our mass as a volume integral of the density over the whole volume. And kind of to write this out a little bit more explicitly, what I mean by that is if we integrate over x, y, and z in Cartesian coordinates, for example, we would have a density that depends on where you are in space. So I have a density that depends on x, y, and z. And then I'm going to integrate with respect to x, y. Oh, sorry. No commas. X, y, and z. All right, so that's what I mean by a variable density. So this is our density varying over space. And then our volume, this volume integral, we can, instead of writing the shorthand, this is a triple integral with respect to all 3 spatial dimensions. Make sense? Yeah. So I don't think I mentioned this before. This is my first time teaching this class. I usually teach 3500, which is fluid mechanics, and then the classes that come after that. So I'm not going to make promises, but I don't think so. I think this class is more algebra based than triple integral based. Does that make you feel better? It'll come up again. Don't worry. I don't think that the triple integrals that you like the Calc 3 things that you'll see in engineering courses are likely to not be as painful as what you experienced in a math course. I'm not making any promises, but generally speaking, I have found that to be the case. Okay. So please don't like unearth your math traumas just yet. All right. And if you, okay, as a disclaimer, if anybody has issues with math throughout this class, please let me know. I'm happy to slow down if, you want to see more steps or anything. Okay. So if, this is the general case where if density is variable, oftentimes we're going to make the assumption that density is uniform. So when density is variable, problems become very, very complicated very quickly, as you can see. So when density is uniform, what does that mean about this integral? So if we have this integral and density is uniform, that means it's a constant. What can we do with this? Does it need to stay in the integral? No. So we can pull this out of the integral. And then we write this like this. So what is this integral? It's just volume, right? What's your name? Sophia, thank you. So this is just rho v, right? So we are back to our beloved definition of density is just mass over volume, right? Okay. So I mentioned we're going to talk about specific volume, right? Specific volume is just the reciprocal of density. All right. So specific volume, and this is my best job of doing a script EV with my own handwriting, is just 1 over the density, which is, of course, volume over mass, right? So this all checks out because a specific quantity is the quantity divided by mass. So specific volume is volume divided by mass, which just so happens to be 1 over density. Okay. I've already, let me see. So if we have a uniform specific volume, that means we have a uniform density. So that means that we have our volume over mass, and that we can also rearrange this to write that the volume is mass times the specific volume. Okay. I think I've already said this a couple of times, but I have it formally in the notes right here. So this V with a slash through it is how I'm going to denote volume. And then a regular V is velocity. I'll also just make mention of this now. I try to do a good job with keeping things straight in the notes, but if you're ever confused, like, are you talking about volume or velocity? Or oftentimes, it can be tricky. Are you talking about density or pressure? I'll try to keep them distinct, but my feelings aren't hurt if it's not clear. I'll redo my handwriting. So just don't be afraid to ask. Okay. Who can tell me what the dimensions of specific volume might be? So we have volume over mass, right? What are the primary units of volume? Do we remember? Yeah, it's length cubed. Remind me your name again. Can you say it again? Mosuda? Is that right? Okay, thank you. And then mass is already a primary unit, right? So we keep mass down here. All right, so that means that the units for specific volume are going to be things like meters cubed per kilogram or feet cubed per pound of mass, and so on and so forth. And so that's all I'm going to tell you guys at this point about specific volume. Make sense? Cool. Okay. Next, we are going to talk about pressure. All right, so pressure is the normal force exerted by a fluid per unit area. A force per area is a stress, so this is just like stress, except for we only have a normal component to it. All right, so stress can act, or does act, I guess I should say. No, stress acts normally and tangentially. Pressure only has a normal line of action. Okay. So just to clarify what I mean by that. So if we have some surface, so this is our surface. Generally, any force that we might have on this surface will have a normal component, and it'll also have a tangential component. So this one is, oop, that's not what I want. And it's acting perpendicular to the surface. And then our tangential force, on the other hand, is going to act tangentially to the surface. Does this make sense, kind of how you break it down in normal tangent components? Okay, awesome. So pressure only involves normal forces, and it is, bless you. So pressure is equal to our normal force divided by area, or Fn over A. Okay? So if I were to draw kind of what pressure is going to look like on a general body, if this is our random blobby shape that we have, pressure is going to act always normal to the body. Okay? So that's our pressure forces. Okay? For a fluid at rest, what do you guys think? You probably already know the answer to this if you've ever swam in a pool or just experienced life on Earth. What happens to the pressure as you increase in depth, as you go down in depth? It increases, right? Can anybody, you don't need to give me equations for this, but just conceptually, why does that happen? It's kind of a meta question. Oh yeah, go ahead. Yes. Is it Owen? Leo, sorry. There's so many of you. I'm trying. Thank you, Leo. Yes, that's exactly why. So the reason for this is the increased weight of the fluid above you. Or the submerged area. All right, so if you were to look at, a column of water, here's our column of water. I'm going to draw it twice equivalently. So if, for example, we are considering this spot on our column of water versus this spot on our column of water, calculating the pressure on that initial one, we are going to calculate that by using the mass of the water above us and then the mass of the water above us here. So I'm going to call this P1 and I'll call this P2. So the weight of the water, rho MV, in this left-hand side configuration is a lot less than the weight of the water in the second one. Rho, oh my gosh, you guys, keep me honest, this is wrong. It's rho VG, right? So we have volume 1 and then volume 2, all right? And so volume 2 is greater than volume 1, right? So our pressure is higher in situation 2. Does that make sense? Cool. The other thing that we need to make note of is that pressure is always compressive. All right. So anytime you have pressure, it's always acting onto the body. It's never pulling a body apart, right? Hopefully that's intuitive, but I just wanted to make sure I write it down so that we're all on the same page with that. Another thing that is important to talk about is some of the rules that we'll have to do with pressure. The first one is this governing equation, and I think everybody does this, but if you take ME, if you're an ME student and you take ME 3500 with me, we'll derive where this equation comes from that essentially talks about, the weight of columns of water. But essentially, if you want to know the pressure at any given point, we will be using some reference pressure at the surface plus the density times gravity times the height of the fluid that's above you. All right. And then here, H is the depth from a reference pressure. Does that make sense? So if you imagine that you're under the water in a pool, the pressure that you'll feel at some depth H down is going to be related to the weight of that water that's physically on top of you. Plus you have the atmospheric pressure of the air at the surface of the pool also pressing down on you. Make sense? Okay, cool. All right. Second rule that we want to keep in mind, and this is very handy when we do analysis for pressure related systems, is that if you're in the same fluid and at the same depth, you will automatically have the same pressure. This is called Pascal's law. And that is why, no, that's not a good color. Let's do this one. So because of this, that means that my pressure at A, B, C, D, E, F, and G all have the same pressure, right? So they're all at the same vertical displacement from the surface of this water, and they're in the same fluid, so they're all the same pressure. Same fluid, same depth equals same pressure. All right. And we're going to do some examples and work out kind of how that's especially useful to us when we're doing problems in just a minute. What about pressure, or the pressure at point 8 and point H and point I? What do we think about those pressure values? They're at the same depth, right? Different? Right. So pH is not equal to PI because the fluid is different. Any ideas about which one will have a higher pressure? Is your name Owen? Oh my gosh. Wait, where's Owen? There's an Owen, right? Oh, sorry. Okay. Stuck in my head. Tyler? Ethan. Oh my all right. Anybody have any ideas about which one will have a higher pressure? Yeah. Right, yeah, so mercury is heavier than water, generally speaking. So if you have a volume of mercury on top of you, you'll feel more pressure because that's a higher weight on top of you. Okay, great. Okay. All right. Do you guys want to take a quick break? Oh, yes, thumbs up or question. Okay, yeah, let's take a quick break and then we'll come back and keep talking about pressure. Okay. So dimensions of pressure. Let's do a little bit of practice with our dimensional analysis that we've already done before. So we know that pressure is a force per area. A force we can write as mass times acceleration. And then area, I'm just going to keep as area for now. All right, so mass is already a primary unit, so we can have that as m. Acceleration is a length per time squared. And then area is length squared, right? So we can cancel out one of the lengths and one of the lengths in the numerator and denominator. And we are left with m wait a second. Over LT. All right, and so these units, the units that we have for pressure are 1 Pascal, which is abbreviated PA. That is equal to 1 Newton per meter squared. We can also use a bar, and that is equivalent to 10 to the 5 pascals, or 100 kPa, because kilo is 10 to the 3 or 1,000. So kPa is 1,000 pascals. And then another common unit is 1 pound per square inch. Or PSI. And that is equivalent to 1 pound of force per square inch, like so. Okay, it's important to note here that since pressure changes with depth, and usually when we think about that, we're thinking about like the ocean and things like that, or liquids, I guess. It also changes with altitude too. So we can think about pressure in terms of the atmosphere. So this means that our atmospheric pressure would change depending on your location on the Earth and altitude. However, there are standard reference values for atmospheric pressure at sea level, which is these values that I have down here. So one standard atmosphere is 1 ATM or 101.325 kPa or 14.7 PSI. And those are all equivalent. Yeah, I think so. So the T squared comes from acceleration is like meters per second squared, right? And then area is the length squared. So I just canceled out one of the L's from top to bottom. Does that make sense? Oh, I see. I have a typo. Sorry about that. Yes. Thank you for bearing with me through that. You are correct. What's your name? Jason. Thank you, Jason. Typo catchers are heroes to me. So thank you. Okay. There's a couple different kind of flavors of pressure that we're going to need to be aware of. The actual pressure at any given position is called the absolute pressure. And that terminology will be used kind of in contrast with the way pressure is measured with most devices in the laboratory. So if we are using sensors or gauges in the lab to measure pressure, we're typically measuring gauge pressure, hence the name. Sometimes it's called vacuum pressure, depending on how the absolute pressure is compared to atmospheric pressure. So we're always making some kind of comparison to the surrounding pressures when we're using instruments in the lab. So gauge pressure is the absolute pressure. So this is our absolute pressure. Pressure minus P atmosphere. Whereas vacuum pressure is P atmosphere minus the absolute pressure. All right, so we would typically use gauge pressure used for P greater than or equal to P atmosphere. So if the pressure is greater than what is in the surroundings, and then we'd use vacuum pressure when the opposite is true. So our pressure is less than the atmospheric pressure. All right, so the way this is structured, we're always going to end up with a positive pressure. Okay, if you were to use gauge pressure to measure a pressure less than atmospheric pressure, which you can do, by the way, that is a circumstance in which you would end up with a negative pressure. Okay, which is still allowed. Just wanted to mention that. Okay, in English units, these will be denoted using PSI with a G or an A afterwards. So the A would mean absolute pressure, and then the G is for gauge. As a standard practice, and I recommend that you all do this too, so in solving problems, I'd suggest being very thorough with your notation. So for example, if you have a problem statement that says, at the opening of a column of water connected to a tank, you have atmospheric pressure up at the top. So I would call that P atmosphere. And then if you're given P1 inside of the tank, for example, as a gauge pressure, I will typically write it as this, so I don't forget. Okay. Okay. Okay, so there's two common ways to measure pressure. One of them is a board and tube pressure gauge, and the other is a manometer. I'm going to talk quite a bit about manometers to start with. The most common type of manometer that we'll encounter is a U-tube manometer, and these are used to measure generally small to moderate pressure differences. And they work by essentially changing the height of a column of water in a tube. So you can imagine if the gas in this tank was at really high pressure, you would need that volume of fluid to travel a large distance, and you'd also have to have a lot of fluid in that system. So it's not practical for really high pressure applications, but for small and moderate pressure differences, this is a really good tool to use. Okay, so let's talk about how we might calculate the pressure in this tank based on the height of this fluid in our U-tube manometer. So how can we use H to determine the pressure in the tank? All right. And so I am going to walk you through this um, using some of the things that we've already talked about, pressure, kind of the rules that we talked about. So the first one that I'm going to use, and this is really key to solving pressure problems, is the idea that if we're in the same fluid at the same height, we have the same pressure, right? So that means that at point 1 and point 2, to go from 1 to 2, we stay in this gray fluid and we're at the same elevation. So that means that P1 is equal to P2. So we have same fluid, same height. Does that make sense? Okay. And we know that the pressure, since this is a gas in our tank, the pressure at 1, we're going to assume is the same as the pressure of the gas in that whole tank, right? So P gas is equal to P1. So we're basically arguing that pressure in the gas is uniform throughout. Or another way to say this is between the top of the tank and the bottom of the tank, the pressure between these two places is negligible because the density of the gas is just not high enough for this to be a big difference. Technically there would be, but we're going to assume that it's not. Does that make sense? Okay, so we know that pressure at 1 is the pressure we want to find, and we know that pressure at 1 and 2 are equivalent. All right, so basically what we need to do is we need to do a force balance at point 2, okay? To find P2. All right, so I'm going to draw another picture zoomed in on point 2 and then the column of water above it. So this is point 2. And then we have a column of fluid above it. So here's what we're looking at, is this right here. All right, and so I want to draw the forces on essentially this body that I have, right? So I'm going to have atmospheric force on top, and the force of atmospheric pressure is P atmosphere times the area, right? Because pressure is a force per area. So if we want to get the resulting force of a pressure, we just multiply by the area, right? And I should note that this is our cross-sectional area A. And then on the bottom, I have P2 times A, right? Am I missing any forces? So we have gravity, right? So we're going to have our body force. So we have the weight of this fluid. Okay? So what I've drawn right here is essentially kind of cartoonized free body diagram, right? Does this feel okay for everybody? The forces on it? Okay, great. So I'm going to do a sum of the forces in the z direction. And what should the sum of the forces be equal to? What's the right-hand side usually equal to? Do you remember? So in general, the sum of the forces is equal to mass times acceleration. Is this body accelerating? It's just static, right? So it has a mass, but acceleration is 0. All right, so this is equal to 0. All right, so now that all that's left to do is I just need to sum up all of my z direction forces. So those are all my vertical forces, and then I set them equal to 0. All right, so going from top to bottom, I have minus P atmosphere times A minus the weight plus P2 times A is equal to 0. Do we feel good about the signs? So anything pointing down has a negative sign, pointing up is positive. All right, I want to do a little bit more work with this weight. What's another way that I could write the weight using the density of the fluid? Any ideas? So weight is mass times gravity. So I have mg. How can I write mass using density? No one? Density is mass over volume, right? So I can do, yeah. Yes, great, thank you. Sophia. Okay. Hope is not lost for me. Okay, density times volume. So that's our mass times gravity. Okay, so how can I write my volume of this? And I'm going to make a little note here. This is H, this is our column of the fluid height, right? So how would I write the volume for that cylinder? Yeah, just area times height. Thank you, Sophia. So I feel like I wrote aggressively large here. I'm sorry. So I have P atmosphere times A minus rho, and then H times A is our volume times G plus P2A is equal to 0. All right, now I notice that I have A in all three of these terms. So I'm going to divide through by it. I can do this because area is not 0. All right, I'm not dividing by 0. This is totally fine. All right, so I'm going to divide through by A and cancel these out, right? And now I can just solve for P2, right? So I'm going to solve for P2. And I get that P2 is equal to, what I'm going to do is I'm just going to take those first two terms on the left-hand side, I'm going to add them over to the right-hand side. So I have P atmosphere plus rho Hg, which is the same thing as rho GH, right? So we get back our standard kind of equation for calculating pressure at a location. All right, so I calculated what the pressure is in this tank using the height of that column of fluid, the density of the fluid, and the value of atmospheric pressure. Okay. Does this make sense how the YouTube manometer is working? So just to recap, we're going to make use of, generally when you solve these problems, you want to find kind of a line where you have a points 1 and 2 and the pressures are equivalent. And then you can do a force balance at one of those points. In this example, it was 0.2. Does that make sense? Questions on this one? Okay. Fantastic. That was just a single fluid, right, where we were analyzing pressure. You could have a situation where you have fluids stacked up upon each other. So if they're not mixable fluids, like oil and water, for example, you can have layers of them. So you might want to calculate the pressure beneath layered different types of fluids. All right. So if we wanted to do that, what we would do is I would suggest, if I want to find pressure at 1, so we want to find this. So what we're going to do is we're going to start at the top and work our way down. And the name of the game is we are going to figure out the pressures at each of the fluid interfaces. So I'm going to call this location A, and I'm going to call this location B. Who can tell me what the pressure at A is? Using essentially the same version of that equation that I put right above. Oh, and let's call this density 1, density 2, and density 3. Any ideas? We have P atmosphere to start with, right? And then what do we add to it? Yeah, rho 1, H1, G. I did not see who said that. Mark, thank you. Great. Okay, and then what about PB? PB is a little, oh wait, I heard something. Yeah, right, amazing. So we have PA plus rho 2, H2, G. Remind me your name? Emma. Great job, Emma. Okay, so I was almost ready to give you a hint that the reference pressure is not always atmospheric pressure, right? So here our reference pressure is pressure at A, okay? Because we're just looking at this section. And this one, we're just looking at this section, right? Excellent. Okay, what about this third one? How can I write an equation for P1 now? What's our reference pressure here? PB? Yeah, great. So we've got PB plus our density of our fluid above us, which is rho 3, H3, G. Right? Okay, so now we kind of have to combine all of these things together, essentially just by substituting. All right, so what I'm going to do first is I am going to I want to find P1 in the end, right? So I will take this equation for P1 and I'll notice that I have PB here and I'm going to substitute in this expression. Okay, so I have P1 is equal to PB, which is PA plus rho 2 H2G plus rho 3 H3G. Okay, so we're a little bit closer, but we still have PA in here and we don't know that one. That's not in terms of the quantities we know. So I'm going to say, okay, great. I need PA and I'm going to substitute in this expression for PA. So we have that P1 is equal to PA, which is P atmosphere plus rho 1 H1 G plus rho 2 H2 G plus rho 3 H3 G. Right? And that's it. All right, so we found our pressure at 1 by using our atmospheric pressure and then the densities and the heights of each of those fluids in our layered up system. Does that process feel okay? More or less? Questions on that? Okay. Okay, so we've kind of talked about using manometers for finding static pressure in tanks and things like that. They're also really useful for measuring pressure drops against flows in pipes, for example. And so the way this kind of is set up is using a system like this picture down here. So here we have flow going through this larger section here. And we're interested to figure out what the difference is in pressure between P1 and P2, or in between 0.1 and 0.2. So we want to find P1 minus P2. So we want to find P1 minus P2. Okay. And this fluid, we have two fluids here. We have fluid 1 is the blue color, and then we have fluid 2 is this like reddish orange. All right. And so what we're going to do is we're going to use the same process as what we did before. So the first thing we're going to do is identify a point that has the same height in the same fluid. All right. So does anybody have any ideas for like which letters on this system we might use to start things off? Yeah, A and B. That's great. So we're going to use A and B. So we have that PA is equal to PB because we have same fluid at the same height. Right? Okay, and then what we can do is we can connect the pressure at 1 to PA and then the pressure at 2 to PB. All right, so we're going to work on both sides of this equation at once, essentially. So let's start with the left-hand side. So we're going to do PA. So PA is going to be equal to our reference pressure, which is going to be the pressure at 1, right? Plus we have the density of our fluid for fluid 1. What is the height here? So we just want our vertical height. Yeah, so we've got H plus A times G. All right, so that is this segment here. And then now we're going to do the exact same thing with this point here. Now this one is a little bit trickier because we have layered fluid, right? So what about pressure at B? Does someone want to walk me through what this one's going to look like? And before we do that, I just want to put a quick pause on this. So when we did this layered fluid system, you'll notice that we ended up with our reference pressure at the very top plus rho GH of each of the individual layers summed together, right? Which kind of makes sense because we're adding up the weight of the individual layers over top of us. Okay, so we're going to do the exact same thing here, except for now we just have 2 layers, right? So I have, what would I use as my reference pressure for this one? Yeah, so we've got P2 plus, what do we have in our first layer? Rho 1, what's our height? A times G. And then what about our second layer? Rho 2, HG. Fantastic. Does this make sense? Okay, cool. So we already know that PA equals PB. So I'm going to just equate 1 and 2. So I'm going to set number 1 and number 2 equal to each other. And I have P1 plus rho 1 H plus A times G is equal to P2 plus rho 1 AG plus rho 2 HG. Now remember, I want to find P1 minus P2. So what I'm going to do is I'm going to subtract P2 to move it over to the left-hand side, and then I'm going to move the rho 1 H plus A G over to the right-hand side. All right, so I have P1 minus P2 is equal to rho 1 A G plus rho 2 HG minus rho 1 H plus A G. Can anybody tell me how this simplifies? There's two terms that cancel each other out here. So gravity is in all three terms. I could divide through by gravity, but then I'd end up with P1 over minus P2 divided by G. But do you see this term balance up anywhere or show up anywhere else with a minus sign in front? So I've got minus P1 AG right here. So these cancel each other out. So then I end up with rho 2 HG minus rho 1 HG. I can factor out that HG and I just have rho 2 minus rho 1 HG. That was a little more complicated. How do we feel about that one? It's not too bad, right? Questions? No? Okay. We're gonna do an example. This is very practical. Okay, we are needing to select a wall mount flex tube well type U-tube manometer, which is a real mouthful. And we want to measure gauge pressures in the range of 0 to 5 kPa. So essentially we want to be able to handle pressures that go up to 5 kilopascals. So let's keep that in mind. That's an important tidbit of information. So we want something that's a wall mount. And then we also want to measure up to 5 kPa. And so on the website, we basically have a chart that will help us figure out what part number or model number we need. And this chart will give us a few different options. So I'm going to just kind of write down the system. So our model number is going to look like this. So we're going to have the series number dash the 8 value. It's confusing that it's called 8, and then 8 is also an option. Or I'm sorry. Hang on. Series, then range, which could be 8, then fluid, and then finally options. So for example, we could have a part number that selects these things, and it would look like 1230-8-WM-B. Okay, that makes sense? Kind of how you use the chart. Okay, we have a couple of other requirements for our system. So we want to use a 1/8 inch pipe thread for our application. So we want to keep that in mind. And then we want to pick a system that will work using water, mercury, or oil as the fluid in our manometer. So we want to spec this out for each of those 3 working fluids. Okay. Okay, so looking at this chart, our series, we can either choose wall mount or panel mount. We already know that it needs to be a wall mount system, so we're committed to 1230. All of the ones that we're going to choose are going to start with 1230. The second one is our range. So this is the most important one that we want to look at. So this WC means water column. And what that means is this is the height of changes in height that the barometer can accommodate. All right. So it can measure, for example, this one, the max H that our barometer will measure is 24 inches. Okay. So we're going to need to figure out what height that max pressure we want to measure equates to in H, and make sure that our system can handle that. Does that make sense? Okay, so let's do it. So this is a sketch of what our manometer is going to look like. We're going to connect it to our pressure of that pink gas P. And we want to find what this H is, right? So we know that P1 is equal to P2 because we have the same fluid, same elevation. Right? And we know that P is equal to P1 because it's a gas in this tank, same argument as what we made before. And then P2 is equal to, we're going to assume this is atmospheric pressure up top. We have P atmosphere plus rho of our fluid, GH. Right? So P2 minus P atmosphere is equal to rho of that fluid that we choose times GH. So we're going to remember P1 equals P2. So we have P1 minus P atmosphere is equal to rho of our fluid, GH. And then we also know that P1 is equal to the pressure we want to measure. So we have that P minus P atmosphere is equal to rho of our fluid, G times H. What is P minus P atmosphere? Is that any kind of a special pressure? It could be depending on if P is higher than P atmosphere. So this is just the gauge pressure. Okay, related to vacuum pressure. All right, so remember that this is P gauge, which is what we want to measure, right? All right, so we have that P gauge is equal to density of our fluid, GH, and we want to calculate H in this system, right? So we have that H is just our gauge pressure divided by the density of our fluid times G. Okay. All right, so what we're going to do, we have this equation, and this is what we're going to use for the rest of kind of sorting out this problem. We're going to figure out what the H works out to be given those three different fluids in our manometer. And then does anybody have any ideas of what we should use for the pressure? Is there like a worst case scenario that we should consider for this? Yeah, 5 kilopascals. So that's the maximum pressure that we'd want to measure. And that's the maximum pressure is going to be the highest vertical displacement on our manometers. We want to make sure that the fluid's not, you know, overflowing out the end of the system. All right, so that's great. So using our water as our first fluid, what we're going to do is we're going to use H for H2O is equal to P gauge over rho H2O times G. And we're going to use 5 kPa since that's the max. All right. Okay. So I've got 5 kPa. I'm going to plug that in here. Density of water is 1,000 kilograms per meter cubed, and gravity is 9.81 meters per second squared. I'm going to do a little bit of unit conversion here. So I know that 1 kPa is 1,000 pascals. So I can cancel out the kPa. So now I have this in terms of pascals. And I know that 1 pascal is 1 Newton per meter squared. So I can now get rid of my pascal on the top and the bottom. I'm left with newtons per meter squared. And finally, I know that 1 Newton per meter squared is 1 kilogram per meter per second squared. So I can cancel out these. And then we can do some more cancellation with units. What color have I not used? I'll do blue. So we have a kilogram in the denominator and the numerator. I have meters per second squared in the denominator and numerator. And oh, you know what? Sorry, I made a mistake here. This is just newtons. So I'm canceling out the Newton, but not the meter squared. All right, so I end up with units of meters. And when I multiply 5 times 1,000 and divide by 1,000 and times 9.81, I get 0.51 meters, which is 51 centimeters. All right. In our chart, in this range, we can choose inches. So they will spec these in inches or in centimeters. So I'm going to convert our centimeters to inches as well. So we'll have 2 options. Okay. So 51 centimeters. And then we're going to multiply this by our conversion. So 1 inch is 2.54 centimeters. So this is 20.1 inches. All right, so our equivalent lengths are 51 centimeters or 21 inches. So we have a choice. The first one, let's spec out the centimeter version. So we're gonna keep series 1230 because it's a wall mount type. So choice 1 is 1230, and that's gonna be the same for choice 2 as well, because we want wall mount for both of them. So for the 51 centimeter option, which range number should we pick? The 60 cm, right? Okay, great. So we're gonna go 60 cm. And then our next component of our part numbers, we want to know the working fluid. So we're going to choose the water/mercury option. So we're going with water. And then the last one is the options. So if you remember, we want a 1/8 pipe thread opening. So we're going to have -C. All right, so for all of these, or for both of these choices, these are going to remain the same. So we're going to keep the W-C. Now let's look at the inches version. So we've got 20.1 is the highest column that we'll need. So which one should we go with? Yeah, 24. Make sense? Okay. let's do this for mercury and then red gauge oil. Do you want to see all of the conversions again? Yeah, okay. So for using mercury, so our height for using mercury is going to be P gauge divided by density of mercury times G. So I'm going to do the same exact process, but now I'm going to swap out my density for mercury, which was given to us up here. Okay. All right. So we're going to keep our 5 kPa, which is our max gauge pressure that we want to measure. Our density of mercury is 13,529 kilograms per meter cubed. And then gravity is 9.81 meters per second still. We're going to do our same conversions again. So we have 1,000 pascals per kilopascal, which allows me to cancel out kilopascals. Then we have 1 pascal is equal to 1 Newton per meter squared. So we can cancel out the pascals. And then we know that 1 Newton is 1 kilogram times meters per second squared. So I can cancel out the newtons here. And then looking at the other leftover units, we have a kilogram in the numerator and denominator. And we have a meter per second squared in the numerator and denominator. And then what we have left is 1 over meter squared divided by 1 over meters cubed, which just gives us meters on the top. All right, so when we calculate 5 times 1,000 divided by 13,529 times 9.81, we end up with 0.038 meters, which is 3.8 centimeters. And then 3.8 centimeters is 1.5 inches. All right, so we have 2 options for this one as well. So we've got option 1 is 1230 M for mercury, and then C for that 1/8 inch thread. And then we're gonna have the same thing for the second one, but we just need to figure out that second number. Okay, so let's keep in mind the 3.8 centimeters first and go back to our chart. What do we think? The 20, yes. So we're gonna do 20 centimeters. And then what about when we look at in inches, we're at 1.5 inches? 8, yes, great. Does that make sense to everybody? All right. Last but not least, let's do red gauge oil. So here we have H of oil is P gauge divided by rho oil G. So we're gonna do all the same conversions that we did before, which I can fill in a second or next time if you guys want me to. But what you end up with is 61.7 centimeters or 24.3 inches. And since we're running low on time, I just want to talk about the differences between these systems and working fluids. So you'll notice that the columns of water change quite a bit in size, right? So for mercury, it's a very small column difference, whereas the red gauge oil is quite a lot. Which one would you rather use if you were trying to measure pressure in a tank? Yeah.
Accuracy.
Yes, that's great. Okay, so talk more about that. Which one is higher accuracy?
Say, probably red gauge oil is higher accuracy.
Yes.
A larger range with a small volume per area.
Right. So just to expound on that a little bit. So when you, the red gauge oil is going to change a lot of height for a little bit of pressure change, right? So that means that it's going to be a lot easier to measure small differences in pressure, which makes this a higher resolution option. Whereas for mercury, a fairly large change in pressure will be a very small change in height of that fluid column. So this is a lower resolution option.